is Russell Malbrough. I wanted to welcome you to the SUNY Global Center. I want to thank you on behalf of the Stony Brook Alumni Association. Can everyone hear me?
Yes, sir.
Wonderful. I want to invite you to the lecture tonight, Professor Stan Metchev, one of our distinguished professors in many regards. I look forward to hearing his talk about the Mayan calendar tonight, which one of our colleagues has heard and really raved about. So looking forward to a wonderful presentation. I just wanted to share, you're here tonight with a number of fellow alumni. We're thankful for the opportunity to get you together in this room, in this space for the evening, for a chance to both network, but also to reconnect with, also to reconnect with one another. So hopefully you've seen other classmates, other friends, and have a chance to meet with one another as well. As Stony Brook alumni, you're part of over 150,000 other individuals throughout the world. We have a strong, robust network. We hope to keep growing that network as volunteers who support our scholarships, support our regional outreach, and who also support various programs that we do on campus. Tonight we have a few of our former board members. One in particular I wanted to acknowledge, but wanted to see if you want to raise your hand. So thank you for coming out as a former board member. We wanted to acknowledge you as a former board member, volunteer. I'm just going to take a moment to introduce our speaker. Stan Metchev has been an assistant professor at Stony Brook in the Department of Physics and Astronomy since 2008. Prior to his arrival at Stony Brook, he has a BA and PhD in astrophysics from Harvard and Caltech. He was also a Spitzer Space Telescope postdoctoral fellow at UCLA between 2005 and 2008. Dr. Metchev's research interests include extrasolar planets, ground dwarfs, novel astronomical instrumentation techniques to study these new fascinating objects. He served as a reviewer for numerous scientific journals and agencies, including Science, the National Science Foundation, NASA, Hubble, and the Spitzer Space Telescopes, among others. He also serves on the board of directors for the New York Astronomy Consortium. Tonight's talk will be entitled 2012 and the End of Times, Myth, Fiction, and Fact. And don't be afraid, there won't be a quiz, but he might ask you some questions, so I prefer you to pay attention. Enjoy your talk.
Thank you, Russell. Everybody can hear me well?
Yeah. Yep.
Thank you all for coming tonight for a talk that will skirt the fringes of science, but at the same time is actually somewhat related to things that I do, so I really enjoy giving it. And it's really my last opportunity to give it, because time is running out for this talk. So unless you've been living under a rock for the past 10 years, you know that there's this upwelling of rumors and discussion that on December 21st, 2012, the world will end, at least according to the ancient Mayans and their calendar. So my role tonight is to discern what is myth, what is fiction, and what is fact in this, and hopefully have you leave with a peace of mind that we'll all survive more than just 10 more days. The most likely scenario that's been purported for the end of the world in 10 days is a cosmic collision of equal proportions, and which is why I'm here being an astronomer, because I understand cosmic collisions, and I know their frequency as well. So the picture that you see in the display is an artist's rendition of what this might look like, and what it's actually shown is would be pretty terrible if it really happened. Before I actually delve into the science bits, I want to show you the introduction to a movie that I'm sure you have heard of, or maybe some of you have even seen. And I'll try that again.
Dinosaurs roamed a lush and fertile planet. A piece of rock just 6 miles wide changed all that. force of 10,000 nuclear weapons. 1 trillion tons of dirt and rock hurtled into the atmosphere, creating a suffocating blanket of dust the sun was powerless to penetrate for 1,000 years. It happened before. It will happen again. It's just a question of when.
This is wonderful Hollywood entertainment. If you have not seen it, highly recommend it. Not because it adheres to the laws of physics, I mind you. Actually, the movie goes on to break those at a rate of 1 a minute for 2 hours. But that first sentence that the narrator says, it has happened before, it will happen again. There's chilling truth in this. And this is more than just Hollywood making a show. By the way, do you know who the narrator is? Charlton Heston. Great choice for a narrator. No matter how your political views square against his, whatever he says, you believe it. So let's get down to reality and things that actually happen in our lifetime. Asteroid collisions are actually everyday matter for scientists at NASA and astronomers. This is an example of one that just happened in 2011, November 9, so just over a year ago. It was 400 meters across. This would actually be a very devastating collision if it really happened. This one came well within the orbit of the moon. In that plot there, the circle is the orbit of the moon. The trajectories, one of the trajectories, the line of the asteroid orbit around the sun. So that's actually closer than the moon to us, and this is the biggest such flyby we've had since 1976. Another one like this, called Apophis, and you'll hear about it a little bit later, is expected in 2029. And that one is potentially even more dangerous, even though a bit smaller. So NASA is realizing this is a reality, and they're trying to track these things any way they can. So all the equipment that they have on Earth, for example, are various optical telescopes that scan the sky all the time. They have radar, and this asteroid, in fact, that passed by a year ago, we got some pretty close-up images, pretty nice close-up images of it. You can actually see in this video the whole rotation of it. And this is now over 28 pictures taken with an Arecibo radio observatory. This is uncomfortably close for an asteroid this size. Even more scarily, in 2008, an asteroid was discovered just 11 hours before it hit the Earth. That was a much smaller asteroid now, which is a good thing. This one actually disintegrated in the atmosphere, and there was just some bits and pieces of it that fell on the ground. But this is the kinds of time scales that sometimes we have to deal with. You discover it, and 12 hours later, it's already colliding. And you can see how close this one came to the Earth. The trajectory was very strongly deflected. Well, this is the one that came in 2009. It was deflected in 2008. Came one that hit the Earth. And here's the one that fell in Sudan in 2008. You can see on the image on the right, there's actually a flash in the center. That's the flash that was recorded by one of the meteorological satellites that orbited the Earth. So this is actually a fairly big explosion happened in the atmosphere. And then on the ground, you had some bits and pieces littered in the end that were found as meteorites on the ground. So fortunately, this thing disintegrated in the atmosphere before it actually impacted. Now, we're not always so lucky. In fact, if you wait long enough, you'll certainly get a bigger collision. It just is the reality of the asteroid size distributions. The bigger ones are less frequent than the smaller ones, and we get many more collisions with small asteroids. But you have probably seen or even visited this place in Arizona called Meteor Crater. This is an asteroid that hit the Earth, a meteorite. The meteorite itself was about 100 meters across and left this big mark in the Arizona desert about 50,000 years ago. Even bigger collisions have happened. The perhaps most famous one is the one that killed the dinosaurs. And now we actually think that we know where this happened in a crater on the Yucatan Peninsula, eerily, actually the location where the Mayans lived. But this was way before the Mayans, 65 million years ago. And this was a very large impact, 10 kilometers across. This is the kind of impact that Charles Heston told us about in the beginning. The one that killed the dinosaurs 65 million years ago. And just another example, these craters, in fact, all over the Earth. This is another one seen in Canada, in northeastern Canada. It's now more or less filled by water, but it's just another example. These things are happening all the time. And none of the ones that we see are more than about 200 million years old, which is as old as this one is. And that's because on Earth we have very active erosion. So wind, water, snow, ice, glaciers will wipe these out after a while, and most of the Earth is covered by water. So if one of these falls in the water, it leaves very little for us to see afterwards, even though the impact at the time might be very severe. The most recent damaging impact happened in Siberia in 1908. And this is it's thought to be a 40-meter large object, possibly a comet, that exploded in the atmosphere above the ground and leveled hundreds and thousands of acres of tundra. Unfortunately, that was not over a populated area. The effects of it, in terms of global climate, were felt for 2 years afterwards all over the world. But the location of the impact suffered much more. This is the biggest we've had in recent history. And again, this is an indication these things happen all the time. All you have to do is look at our moon. It's littered with craters. And that's because the moon does not have erosion, nothing to erase them. So everything that hits it is there for us to see, even the small ones. So actually the distribution of crater size on the moon can tell you what the distribution of asteroids is in the solar system. What I really like about this picture was actually taken by one of my non-majors undergrad students. She was a freshman in my course a year and a half ago. We have this 14-inch telescope on the roof of the Earth and Space Sciences building, which is a wonderful public outreach and education tool. So she walked up to the telescope, and I've been making everybody look at the eyepiece. And I know that if I want to take an astronomical picture, I have to put a complex camera on the back end and cool it to some cryogenic temperatures and so on. She just walks up with her BlackBerry Android droid and puts it against the eyepiece and snaps this thing. Like, my goodness. She just handed me a wonderful outreach tool, and I was not even aware of it. So this is stuff I'm learning from my non-majors. I think she was a psychology major, a freshman. So ever since, I've encouraged all my students to take pictures like this through our telescopes, so they have pictures of Saturn, Jupiter, Venus, name it, whatever. So, to stress this, we know impacts are a cosmic uncertainty. We know over 100 craters known on the Earth. None of them are very old. Most of them we don't see after about 200 million years, and that's because of erosion. And most of them we don't see, period, because they probably happen over ocean. Anyway. To be a little bit more technical about this is a slide that I showed these same non-major students of mine. It shows the distribution of impactor size and impactor frequency. So the upper left of the diagram, we have small impactors, high frequency. So a 1 meter asteroid or 1 meter meteorite will hit the Earth about once every 10 days or so. A 10-kilometer asteroid, like the one that killed dinosaurs, will hit the Earth about once every 100 million years or so. And there's a continuum distribution of this. So fortunately for us, the very large ones that cause mass extinctions are very rare. The last one happened about 65 million years ago. And if you compare them to things that we actually see on the surface of the Earth now, this is where the Arizona crater impactor is, and this is where the one that killed dinosaurs is. Now, there is some additional evidence from biology that suggests that impacts of a certain size might actually happen, a large enough size, might actually happen with some frequency to them, some periodicity, which was relatively new evidence. It was published in 2005, so this is another one of those complicated graphs. which shows at the very top graph that the green and blue line, that's just the number of genera. A genus is some sort of essentially a subspecies of in biology. So this tells you essentially the biological diversity on the Earth as a function of time in the past. So time runs backwards to the right. And you can see some of the main geological eras, such as the Triassic and Jurassic and so on the very bottom of the scale. So you can see there's a very large explosion of the biodiversity in the recent several tens of millions of years. You can subtract that trend, the overall growth in biodiversity, and then in that panel called C, you actually get the residual, which now looks like it has an oscillation to it. And the authors in this case have actually fit a sinusoid with a period of 62 million years. And this tells you that they detect from evidence that there's approximately a 62 million year period between major impacts that cause mass, not just mass destruction, but they kill species, major damage to the biodiversity. So what's worrying is that the last major impact of this size was 65 million years ago, and the period is 62 million years, plus or minus 3. So it looks like, well, maybe we're overdue for one at this point. So maybe we should be worrying as much as some people might be.
That's not clear, because are you suggesting a cause for that periodicity?
No, I'm not suggesting a cause. Just an observation. There is some.
But there's no theory or hypothetical theory that will justify a $62 million periodicity.
That is a good point. So you're saying this is just an observation. What is the explanation for it?
I mean, God didn't decide 62 million years is the frequency that they should occur, and you have no hypothesis to defend it.
So that's not exactly true. There have been actually some hypotheses having to do with the orbit of the sun around the galactic center. That's a 200 million year orbit, and the sun will go above and below the galactic plane, and occasionally will cross spiral arms. When the sun crosses a spiral arm, it enters a higher density region in the galaxy. So then you could potentially encounter things like molecular gas and stars that could deflect.
And that corresponds with 62 million years.
It doesn't, and that's the point. It does not. Actually, there's insufficient evidence to prove it does.
Thanks. Thank you.
That's a very good point.
Thank you.
So there may be a reason for us to worry, at least based on the empirical evidence. But as we saw now, that's actually when you actually try to explain why this, it's not clear why this may be happening. And so then come the doomsday sayers, and there's this observation of the Mayan calendar is supposed to end at the end of this year, 2012. So maybe this will, in fact, coincide with the potential mass cataclysm that we've seen in the past. So I have to give you a little bit of an overview of what the Mayan calendar is, and then the various interpretations. It's actually quite interesting from an anthropological standpoint. I've learned a lot actually reading through this, and since all of you are probably non-astronomers, this might even be closer to what you're interested in. So this is an example of the Mayan calendar. This copy is called the Madrid Codex. It was essentially taken by the conquistadors when they came to Mesoamerica and brought back to Spain. And it's a depiction of a calendar. It was created about 1530 AD, so after the Conquista. And it depicts the 260-day divinatory calendar. This is a cycle that's more or less like a year, 365 days, but quite a bit shorter. And here, the days are marked by dots, and you can see those black dots on the side. That's what marks the days on the calendar. And the thing to note is that in all these calendars, there's actually 5 cardinal directions. And the white circles show you east, west, north, south, and the 5th one is the center. That was one of their cardinal directions, the center. And the center actually turns out to be quite fundamental to the discussion of the calendar now. The calendar itself was likely invented by the predecessors of the Mayans, and the Mesoamerican populations tended to inherit and improve